Welcome to this explainer. When you look at a massive petrochemical plant or a power station, it's easy to think the absolute hardest part is just getting those giant pieces of heavy machinery onto the site. But actually, setting them down is really just the beginning. Today, we're diving into a highly precise, absolutely crucial step in industrial construction known as leveling. We're talking about those invisible micro-adjustments that literally keep these multi-million-dollar facilities from vibrating themselves to pieces.
To kick things off, let's think about a super relatable everyday problem. Have you ever sat down at a restaurant or maybe at your desk and realized the table is wobbly? It's so annoying, right? So what do? You probably grab a napkin, maybe a folded up piece of paper or a cardboard coaster, and you just wedge it right under that floating leg. You do this because even though the floor looks perfectly flat, it isn't. You are making a micro adjustment to stabilize the whole structure. Keep that exact concept in your head because it is the fundamental principle of everything we're talking about today. So, taking that everyday fix, the folded paper under a chair leg, and scaling it way, way up brings us to plant engineering. In heavy industry, civil engineers pour these massive concrete support pads for equipment to sit on. But here's the catch. Even with a flawlessly poured concrete foundation, when you lower a multi-ton piece of stationary equipment, like a towering vertical vessel, onto that pad, it can still have a slight tilt. The concrete might be off by a tiny fraction of a millimeter, or maybe the base of the equipment itself has microscopic variations. The fix? It's exactly like that folded piece of paper, just engineered for heavy industry. Let's take a quick look at where leveling actually falls in the construction sequence. First up, we have equipment erection. That's when the cranes bring the massive machine down onto the foundation. Right after that comes leveling. Then we hit inspection to verify the work, and finally, tightening the anchor bolts. It's a strict order. If you skip leveling or do it out of sequence, you're going to permanently lock a tilted machine right into a solid concrete foundation, which is a massive headache. So what exactly do we mean by leveling? Formally, leveling is the process of aligning massive stationary equipment to perfect horizontal and vertical planes by inserting micro adjustments under the base plate. The big takeaway here is that gravity alone just isn't going to cut it. We have to actively intervene and correct any tilt before locking the equipment down. If a tower leans even slightly or a high-speed pump is angled just a hair, the internal stress and vibrations over time will absolutely cause catastrophic mechanical failures. And the tool we use for this intervention is honestly fascinating. These thin metallic sheets are called shim plates. They are incredibly thin, precision-cut pieces of steel. They almost look like heavy-duty aluminum foil or cardstock, but they are incredibly durable metal. In plant engineering, there are no folded napkins. We use these highly engineered shim plates to make those crucial sub-millimeter adjustments. This is where the magic happens. You literally insert these ultra-thin shim plates directly under the base plate of the equipment, right between the machine's foot and the concrete foundation. By stacking shims of different ultra-thin dimensions, an engineer can dial in the exact thickness needed to totally eliminate any tilt. It is a super meticulous, hands-on process. You test it, add a shim, check the level, and tweak it until it's absolutely 100% perfect. Section 2. Proving perfection. Level and verticality inspection. To actually pass this rigorous inspection, we primarily need to measure what's called vertical inclination. Basically, this is the exact measurement of how much a piece of equipment leans or tilts away from a true, perfect vertical axis. Picture a perfectly straight plumb line dropping straight down from the sky. The vertical inclination is the gap between that perfect line and the actual side of our equipment. We've got to make absolutely sure the machine isn't leaning. We definitely do not want a leaning tower of pieces situation on our site. To prove everything is perfect, engineers use an official inspection format just like this one. It's a very structured document where inspectors have to verify and sign off on two main things. First, the equipment base elevation, which ensures the machine is sitting at the exact right height relative to the rest of the plant. And right below that, the vertical inclination. You can see the diagrams at the top showing exactly how those measurements are taken from the top reference point all the way down to the base of a tall vessel. It is a very formal, documented proof of perfection. Now, the crazy part here is just how strict these inspections really are. The process covers the base elevation and verticality checks, but the real kicker is those strict tolerances. In a lot of industrial projects, the maximum allowed deviation is practically microscopic. We're talking an allowance of maybe 0.6 millimeters of tilt for every 1 meter of height.
To put that into perspective, 0.6 millimeters is roughly the thickness of a mechanical pencil lead. So if a machine is 10 meters tall, the absolute maximum it can lean at the very top is just 6 millimeters. That is an insane level of precision, and it's all made possible by those tiny metal shim plates we saw earlier. Of course, you can't just eyeball a 0.6 millimeter deviation, and a standard tape measure definitely won't cut it either. To measure this, engineers use an incredibly precise optical instrument called a theodolite. A surveyor sets it up and projects a mathematically perfect, laser-straight vertical reference line against the equipment. By comparing the top of the machine to the bottom against this optical line, any tiny gap or lean is instantly visible. If the theodolite spots a deviation that's out of tolerance, well, it's right back to the shim plates for more micro adjustments. Once the theodolite confirms that the vertical inclination is perfectly within that tiny microscopic tolerance and the inspection document is officially signed off by everyone, we finally reach the last stage, the final lockdown. Those massive anchor bolts sticking out of the concrete foundation and passing through the equipment's baseplate, they are finally aggressively tightened down with massive nuts. Because we waited to tighten these until after the shim plates perfectly leveled the machine, locking them down now secures everything in flawless vertical alignment. The machine is now permanently, perfectly straight. As we wrap up this explainer today, I want to leave you with a thought. What actually happens to an entire industrial plant if just 1 millimeter of tilt is ignored at the foundation? Imagine a massive tower under extreme pressure, or a pump spinning at thousands of revolutions per minute. Industry studies tell us that even a fraction of a millimeter of angular misalignment can slash a machine's bearing life by up to 50%. That one tiny, uncorrected millimeter creates uneven weight distribution, abnormal friction, and vibrations that just get worse the higher up you go. Over months and years, that ignored millimeter leads to shattered seals, ruptured pipes, and literally millions of dollars in unplanned downtime. It's a pretty wild reminder that in the world of heavy industry, massive success relies entirely on the perfection of the smallest micro adjustments. Thanks so much for joining me, and honestly, I hope you never look at a perfectly straight structure the same way again.